Like Scott said, my name is Abodeely. I work with the Idaho National Laboratory. I basically work on sustainability and logistics modeling and modeling integration. So today I'll be discussing our modeling methodologies for performing economic assessments on biomass. Within our group at the INL, our main focus is feedstock supply system logistics, which takes the material lying in the field through various unit operations to a conversion facility. We have these various unit operations. We have harvest and collection, which takes the material from the field and performs some kind of densification through bundling or baling. We have storage, which addresses uncertainties with seasonal harvest times, as well as year-to-year yield variability. We have pre-processing, which changes the format and physical characteristics to improve handling and conversion efficiencies. And then we also have transportation and handling and queuing, which are kind of self-explanatory. You can see the feedstock supply system interfaces with production and conversion systems. And these are items that are researched at other DOE labs, and we work closely with them in order to assess how much biomass is available, where it's located, and how to better format the feedstock to improve conversion. Some of the supply system logistic challenges, there's several up here. We have challenges with physical properties. This includes material deconstruction, which changes the physical format and rheological characteristics of the biomass. Challenges with bulk densities and also with moisture management, which reduces degradation of material. We have issues with supply system equipment, with capacities, operational efficiencies, dry matter losses, an operational window. And then there's also challenges with interfacing with the production and conversion systems. And this includes being able to remove residue sustainably and having access to those stranded resources, as well as providing a quality feedstock to the conversion systems. So the difficulty with overcoming these challenges is to do so in an economically and sustainable manner. Here in this diagram, you can see some of the driving forces in achieving sustainable and economic residue removal. We have the economics that want to drive the yields up, such as logistics, feedstock quality, cost targets that are put out there, that need the yields to be higher in order for the system to be economically viable. And then we have environmental impacts like soil organic carbon, erosion, nutrients that want to push the residue removal lower in order to reduce environmental degradation. But by developing and implementing new agronomic strategies, we're able to increase sustainable residue removal rates to make the system more economically viable. Existing supply systems today struggle with overcoming those challenges that I mentioned earlier. Conventional systems, such as these, struggle with resource availability. They use field-dried feedstocks, which has issues that we'll discuss later. They're also mainly designed to accommodate a single feedstock. One way to address these barriers is to implement a depot system or commodity supply system that takes that biomass and converts it into a uniform format feedstock. And this allows us to have access to those stranded resources, allows those feedstocks with higher moistures to come into the system, and also is capable of handling multiple feedstocks at once. And Chris Wright, who is also from the INL, who's speaking, I think the last session today, will go in a little more detail about these types of systems. So what we've been working on at the INL is developing tools and methodologies for performing comprehensive assessments of supply systems. To be able to do these types of assessments require lots of models and data sets on varying scales. And so what we've developed is this integrated framework approach that allows us to integrate these models and data sets into a single environment. And I should note, to date, Most of our work scope has focused around agricultural systems. So that's what the rest of the presentation will demonstrate some of our capability there, but these same methodologies could be applied to dedicated energy crops as well as woody systems. The integrated framework enables us to perform spatial and temporal assessments. We can perform large-scale assessments here. This is a, it's kind of hard to read there, sustainable, accessible agricultural residues at the county level. This is a data set we put together in support of the billion-ton update. So we can do these large national scale assessments, and then we can also do these field-level assessments that can help support field decision, field management decision-making. Here we formed assessments on the state of Iowa looking at different management practices and how they impact sustainable residue removal. We have a conventional system, a reduced tillage system, a no-till system, and then the actual tillage projections for Iowa. And as expected, the managements with the least soil disruption, the no-till, generated higher yields, higher sustainable yields. So using these types of resource assessments helps us identify the quantity and location of available resources that help support these supply systems. Within the conventional system, yield and feedstock densities are the key drivers for cost. Here we're looking at the spatial impact of yield for a corn stover harvest scenario. And this is using the no-till scenario from the previous slide. I guess going back doesn't work. And you can see there's a wide range of, there we go. Oh, you were? Oh, okay. No, that's fine. There's a wide range of yield across the state, anywhere from half a ton per acre up to almost 3 tons per acre. And then you can also see the amount of acres that were harvested per county ranges from 2,600 up to 9,000 acres. So we have this wide range of variability between yield and the available resources. This shows some of the spatial and temporal impacts that come into play when harvesting residue. In 2009, in Iowa, during the harvest season, we saw significant amounts of rain. And over here we have the harvest progression. You can see that in 2009, harvest didn't start till pretty much the beginning of November and went all the way through the middle of December due to the precipitation. And then in 2010, you can see that this harvest window is much shorter, and it was completed by mid-November. And 2010 was more of an ideal year weather-wise for harvest. So what impact does this have on a conventional system where moisture content needs to be below 15%? We performed a study in northwest Iowa in 2009, 2010. You can see in 2009, over 90% of the bales had moisture content greater than 15%. And then in 2010, it was just the opposite. We had over 90% of the bales that had moisture content less than 15%. So what this is telling us, in 2009, within the conventional system with that moisture constraint, in 2009, we would have had over 90% of the available resource stranded. What we're working on is coupling these supply systems explicitly to the resources to help us get a better understanding of the specifications of the material entering into the supply system. And this places significant requirements on how we manage our data within the model and our modeling approaches. So these are the type of things that we're working on within our integrated framework. Looking at the specifications and performance of storage, it's important to understand the specifications of the material entering into the storage and the impacts that has during the storage process, that the moisture and the storage conditions have on the feedstock while in storage, and what that looks like coming out before being fed into whatever the next unit operation is. So one of the things we're looking at is developing higher fidelity models and data sets that enable us to address the variations in materials specifications and be able to quantify the impact that the moisture and climatic conditions have on the biomass. Similarly, with the depot design, with the depot system, or with the depot, sorry, within the integrated framework, we're developing methods to quantify depot performance through tracking material characteristics entering the depot, inclusion of thermodynamically robust models, and also being able to track material specs for downstream supply and conversion. So what does this mean? Within the depot system, the depot is going to be receiving material from all over the region that's going to have different specifications due to when the material was harvested, how it was harvested, how it was stored, etc. And our integrated framework will be able to, or will enable us to track these various specifications of the material entering the system and how they perform throughout the depot operations. So here's some of the results implementing some of the concepts we just talked about using our integrated framework. As you can see, with the conventional system, we have, as mentioned earlier, we have very little control over the specs prior to the material being delivered to the biorefinery. You can see we have a wide range or high spatial variability in cost. We have between $35 and $80 per dry ton delivered to the biomass, or to the biorefinery. And so again, I just mentioned we have very little control over the spec that's delivered to the biorefinery. In the distributed depot system, the biomass is converted into a more stable uniform format feedstock, which reduces spatial and temporal variability. But this comes with additional costs due to capital and energy inputs. And you can see locally the costs are much higher, but the price range is much more predictable than what you see with the conventional system. And what the depot system allows us to do is it provides greater access to stranded materials and low yielding areas. And once again, we have higher control over the spec delivered to the biorefinery, so the biorefinery knows what they're getting. Here we can see the economic impact of the conventional design system versus the distributed depot design system for Boone County, Iowa. What this data represents is data gathered over a 10-year span. We have the 10 years worth of harvest progression windows, and we use 10 years of climate data to determine the amount of resource that could be gathered during those harvest windows. And you can see that due to the constraints with the conventional system, we're only able to access about 34% of the material generated during that 10-year span. In some years, like 2010, we'd be able to gather all the material that's on the field, or most of the material, and then years like 2009, you'd hardly be able to gather any of the material that's left on the field. So we have that variability going on throughout those 10 years, but overall, we only had 34% of the material that was gathered. And you can see locally the cost is fairly low, but as you start transporting that material across the state or throughout the region, costs significantly increase. With the depot system, you can see costs are initially higher at the local system, but with that uniform format, as we start transporting those resources away from Boone County, costs remain more consistent. And we're able to access all the material versus just that 34%. So in summary, with the conventional design, we have this is an additional risk due to resource availability, uncertainties with material quality and specifications, and cost and variability with the cost. And the depot design system provides us a more stable system where supply and cost risks mirror the grain commodity system, and we have material quality standards in place. So our path forward, we're identifying barriers and limitations to help us quantify those risks. Working on development and implementing additional model and data interfaces to help us bring in more robust models and data sets. Incorporating spatial and temporal commodity material flow networks with current infrastructure, such as the grain commodity system. And then we're also looking at implementing standards for rigorous mass and energy balances of all integrated components. So with that, are there any questions?
We have a minute or two for questions. Any questions? Yes, Jim.
Scott, Dean Jarrett, with the Idaho National Engineering Laboratory and where you are standing up this modeling program, are you in a position, or how far out would you be in the position that agencies or others that actually contact you to do, in essence, the integrated logistics modeling? Is the lab available for us to actually ask for those requests, and if so, when?
Maybe that'd be a better question for Chris to answer. Yeah.
You want to stand up, turn around, Chris?
Sure. So parts of the modeling effort are being rolled out. Some of the work that Jared and Dave Booth, a counterpart of his, have put together on the sustainability pieces are actually being pushed into USDA and being tested, because they use some of the models USDA is already using for soil carbon, erosion, and things like that. And the framework through this integrated modeling approach is taking the best that those models are capable of doing and integrating them so you get a broader picture. So that's being rolled out. As you know, it's going to be tested and put into play because they'd like to use it for policy, for Farm Bill, and other things. So that's starting to become available in a broader community with the ARS stations and so on. The logistics modeling piece, most of it's done for internal SOT development, state of technology, and mapping where we're going and are we meeting targets. And oftentimes the usability of the models aren't such that they're very distributable, I guess. But we have a lot of requests, and we're looking at the ways and working with DOE to determine whether these models are going to be developed specifically to be used in community use and for extensions and so on. And so right now, I think that's still being negotiated because much of the funding that's come to us is to make sure that we're targeting and meeting our target. And the development is also showing theory and where the progression of the supply system might be going and putting some legs under that. As Jared's pointing out here, moving away from more conventional systems to, broader commodity type systems. So I don't have an answer as to when it might come out, but there's been plenty of requests from us to DOE to support that effort. And likely the way it'll happen, like anything today, is the models will be web-based and then be able to be distributed accordingly. So if there's a broader need for that, then please continue to communicate with us through our website or directly, and we can make those offers out. We do direct business with a lot of folks that have specific needs for logistics, and that continues to go. It's not on a broader basis.
Thanks, Chris. Any other questions real quick? Very good. Thanks, Jared.